something is happening to Earth. The magnetic shield that keeps our world breathable and bright is changing fast. At the same moment, a wanderer from another star system named 3i Atlas is sweeping past the Sunday coincidence or choreography. The timing is razor neat, the questions are loud, and the numbers are not interested in our comfort. Tonight we chase data, not drama, and test every idea until it either stands or snaps. Stay with me as we follow the evidence wherever it leads. Tap like, hit subscribe, and turn on notifications so you do not miss the next move in this investigation. Start with the paradox. Earth's field is not a static bubble. It is a living structure born in a global ocean of liquid iron that spins far beneath your feet. For most of history, that field drifted, strengthened, and faded on timescales that felt almost geological. Then the graphs bent. The measured global dipole has declined since the 19th century. The South Atlantic Anomaly has grown, from a technical curiosity into a practical headache. Satellites crossing that region take extra radiation on the chin. Engineers plan around it. Suddenly, this is not a textbook footnote. It is a current event. Now roll the clock to late October in the current year. 3i Atlas reaches perihelion near 1 4/10 astronomical units. That is comfortably outside Earth's orbit. At closest approach to our planet in December, the distance stays vast. No collision risk, no gravitational theatrics, just a visitor from deep time who will never return. The geometry is harmless, the opportunity is huge, and the timing is provocative enough to make even a cautious mind raise an eyebrow. That is the hook that brought millions of eyes to the sky and to this story. Physics asks for a mechanism, not a mood. If a passing comet changes core dynamics, there must be a way for that influence to cross 3,000 kilometers of rock and mantle, then matter at the scale of planetary energy. That is a tall order. Most experts say the energy does not add up. The timescales do not line up. The data on field decline began long before anyone logged the first images of this interstellar traveler. That is the sober view, and we will treat it with respect. We will also pressure test it, because skepticism does not mean refusal, it means work. What does a serious investigation look like here? It begins with measurement. We will show you how satellites like the European constellation that maps the field from pole to pole transformed hand-drawn contour lines into live, high-resolution portraits. We will pull on records from observatories and ships and aircraft and phones that all lean on the same global magnetic model. We will revisit the emergency update that arrived in 2019 when the pole sprinted towards Siberia faster than expected. Evidence before ego. That is the rule. Then we will meet the visitor properly. Interstellar objects do not announce themselves. With fireworks, they appear as faint motions against a starry grid, betraying their origin only when the math of the orbit refuses to close. The first one we saw shocked people by behaving like nothing we knew. The second looked comfortingly normal. 3i Atlas lands in the middle. It is a bona fide comet with gas and dust and a tail, yet it started shedding water far from the sun, and its scattered light hints at dust unlike the usual solar system recipe. Harmless, strange, valuable. Between these two threads sits the tension that powers the next 2 hours. On one side, a planetary shield that seems to be in a lively mood, complete with a weak zone the size of continents, and a pole that will not sit still. On the other side, a messenger from elsewhere, passing through at the perfect moment to ignite our ape-brain hunger for patterns. If the overlap is a coincidence, fine. But coincidences can mislead, and sometimes they can motivate better questions. We will ask them in plain language, and we will keep speculation clearly labelled, so your trust never has to guess. Here is the pact with you. We will not bury you in jargon. When we say geodynamo, we will show the picture in your mind. When we say reversed flux patch, we will give you a river metaphor that holds. When we say induction, we will show how currents in the sky can tickle wires on the ground and why that signal fades with depth long before it reaches the core. We will also tell you exactly what would count as convincing evidence for any real link and what would not. That way you can judge the claims you hear with the same tools the pros use. One more promise. We will not confuse intrigue with danger. 3i Atlas is a story of knowledge, not threat. The field over your head still does its job. Aircraft still fly. Satellites still work, with adjustments. The alarm here is intellectual. The world is stranger and more dynamic than the tidy diagram suggested. That is not a reason to panic. It is a reason to pay attention. The next parts bring receipts, numbers, maps, orbits, laboratory-grade humility, and somewhere in the weave of those threads we will find an answer worthy of your time. The investigation starts now. You live under an invisible ocean that flows without water and never sleeps. Earth's magnetic field surrounds the planet and shapes space itself into a teardrop that points away from the Sunday. On the day side, the field is pressed inward by solar wind. On the night side, it stretches into a long tail that reaches far beyond the moon. This is not poetry. It is architecture. When charged particles from the sun slam into that structure, most are turned aside. Some spiral along field lines toward the poles and light the sky. We call those curtains auroras, and they are the gentle edge of a very rough story. Where does the field come from? Not from bar magnets buried in rock. It is born in a global sea of liquid iron, more than 2,000 kilometers thick, that swirls around the solid inner core. Heat leaks outward from the deep earth. Lighter elements rise, heavier ones sink. The planet rotates and twists the flow into helical paths. Moving metal conducts electricity. Moving electricity makes magnetism. That feedback loop is the geodynamo. It has run for billions of years, sometimes stronger, sometimes weaker, sometimes flipping polarity entirely. Life does not care about polarity. Life cares that the field exists and holds. Why does it matter so much? The sun is not a polite neighbor. It sheds a constant wind of plasma and sometimes throws tantrums that hurl dense clouds of magnetized particles toward us at hundreds of kilometers per second. Without a magnetic shield and a thick atmosphere, that wind can strip a world. Mars is the cautionary tale. Its global field died long ago, and the sky took its air away grain by grain. Earth kept its field and kept its air. That is the headline. Now the detail that brings us to today, the strength of. The global dipole has trended downward since the 1840s by on the order of 9%. The change is not uniform. In some places, the field has hardly budged. In others, it has thinned enough that satellites feel the hit. Over the South Atlantic and parts of South America and Southern Africa, the field weakens into a broad dent called the South Atlantic Anomaly. Spacecraft that pass through this zone see more energetic particles than their designers once expected. Engineers schedule certain operations outside that corridor. Astronauts orient sensitive hardware away from the flux. Ground crews plan around space weather forecasts the way pilots plan around storms. Field change is normal. Maps of declination and inclination have drifted since people first put iron needles on pivots. What is new is the tempo. The anomaly's footprint has spread over the past decade, and a second weak cell grew under Southwest Africa. Meanwhile, the North Magnetic Pole has hustled toward Siberia, fast enough to complicate navigation tables. When a system this grand moves on human time, people notice. Textbooks that taught century-scale calm now read like snapshots from a quieter era. That does not mean catastrophe. It means we need better models and more honest uncertainty. Everyday life already depends on the magnetic field in quiet ways you rarely see. Survey crews correct compasses to keep property lines straight. Aircraft and ships use magnetic headings as a cross-check when satellite navigation degrades. Oil and gas drillers steer boreholes with downhole magnetometers. Your phone's orientation sensor leans on a world map of the field to figure out which way you face. When that map drifts faster than the scheduled update cycle, tiny errors add up. The fix is simple. Update the model more often and fly smarter. The deeper lesson is bigger. Our planet's shield is a living thing, and the future is not guaranteed to match the past. If you want a single picture to carry forward, keep this one. Imagine the dipole as the broad, simple melody that carries across the concert hall. Now imagine smaller instruments weaving around it. Those are higher-order structures called multipoles, and they can grow and fade as core flows change. When the side instruments get loud, the melody at the surface can sound thinner, even if the orchestra in the pit is still roaring. Satellites are close to the stage. They hear every change. We hear only the parts that reach the balcony. That is why ground life still feels normal while hardware in low Earth orbit complains. Is this the first step toward a polarity flip? Maybe not. Reversals in the rock record stretch across thousands of years, and there have been many false starts called excursions. The present changes could be a strong pulse that later eases. They could also be the early page of a long chapter. The point is not to make a guess. The point is to keep measuring and keep refining the models that connect surface maps to deep flows. The geodynamo is chaotic in the mathematical sense. Small shifts in boundary conditions can steer its path. That is a reason for patience and precision, not for doom. We will spend the next segment inside the instruments and archives that make all of this visible. How do we know the field is weakening here and strengthening there? How do satellites separate crustal magnetism from the deep core signal? How did an emergency update to the global model in 2019 become the quiet headline that forced everyone to pay attention? The answers are not dull. They are the backbone of the entire investigation. Bring that curiosity with you. We are going to use it. If you want to know whether the planet is changing, you start with instruments that do not care how you feel. For Earth's magnetic field, that means a fleet in the sky, a ring of observatories on land and sea, and a global model that ties them together. The magic is not one sensor, but the chorus. When different tools agree, confidence rises. When they disagree, we go back to the bench until the story fits the measurements. In orbit, the European 3-satellite constellation flies like surgeons, not tourists. Each craft carries sensitive magnetometers on long booms to keep the spacecraft's own fields at arm's length. They fly at different heights and inclinations to crisscross the planet under many angles. By sampling the field from multiple altitudes, analysts can peel away layers the way a musician separates tracks in a studio. Shallow signals from the crust fall off quickly with height. Deep signals from the core linger. The comparison lets us isolate the heartbeat far below from the static near the surface. Timing matters as much as placement. Satellites prefer the quiet of the night side and calm space weather. They stitch together millions of short arcs into a global map, while software flags burst from the sun that would muddy the view. Temperature swings and tiny vibrations try to nudge the readings. Calibration sequences catch those gremlins. Redundant sensors cross-check one another. When a spike appears, engineers ask whether it lives in the sky or in the wiring. Trust is built one rejection of noise at a time. On the ground, a century and more of observatories watch the field like tide gauges for magnetism. The instruments are simple in spirit yet exquisite in practice. They point to magnetic north, record the up and down tilt, and log strength around the clock through storms and quiet spells. Far from cities, far from rail lines and heavy industry, these stations provide the long baseline that satellites cannot. Ship logs and lighthouse archives extend the curve back into the age of iron needles and paper charts. The arc of change runs through it all. All of those numbers flow into a common language called a spherical harmonic model. Think of it as a way to describe a complicated shape with a stack of simple melodies. The strongest melody is the dipole, the bar magnet pattern. Higher melodies capture smaller structures that swirl and twist. Mathematicians tune the coefficients until the model imitates the real planet within known errors. Then pilots, phone makers, surveyors, and explorers download the result and trust that north on the map will match north in the world. Every few years, that world magnetic model gets a fresh coat of paint. In most cycles, the update is routine. Then came 2019. The North Magnetic Pole sprinted so fast towards Siberia that errors would have grown uncomfortable before the scheduled revision. So the teams pushed an unscheduled update, a quietly dramatic moment that told professionals the field was not content to wait. The fix was simple to deploy, yet the implication was big. Even our best 5-year plans can be surprised by a restless planet. How do we know the South Atlantic Anomaly is not a mirage? Because satellites feel it, ground stations map its edges, and particle detectors record the punch. Pass through that region, and instruments see more high-energy hits and more corrupted bits. Point the magnetometers down, and the strength chart sags as expected. Track it over years, and the footprint spreads, and a second low appears under Southwest Africa. Independent pipelines confirm the trend. This is what real looks like when you attack it from many sides. To separate deep Earth from near space, analysts must also remove other contributors. The ionosphere and magnetosphere carry their own currents that wax and wane with the sunday. These external fields leave fingerprints that vary with local time and solar cycle. By comparing data taken at different hours and under different solar conditions, and by using companion instruments that measure charged particle density, teams subtract the sky from the stone. What remains is the slow drum of the core and the patchwork of the crust. None of this is a black box. The satellite data are archived. The processing steps are published. The models are versioned, tested, and scored against independent measurements that were not used in the fit. When a new release lands, airlines update flight software. Drill rigs adjust compass corrections. App developers push quiet changes you never notice. That mundane plumbing is a feature, not a flaw. It means the chain from instrument to action is strong and transparent. So when we say the dipole has weakened since the 1840s, that the anomaly over the South Atlantic has grown teeth, and that the pole's sprint forced an extra update, we are not reciting rumor. We are reading a ledger signed by satellites, stations, and ships. The field is moving in ways that matter to machines and to maps. The open question is, why this tempo now? To answer that, we need to visit the anomaly where satellites take a beating and the maps turn weird, then follow the flow lines deeper until they brush the top of the core. Next, we go to the dent in the shield and listen for the story it is trying to tell. If you want to see the shield sag, look where satellites get nervous. Over the South Atlantic and parts of South America and Southern Africa, the magnetic field thins into a wide soft spot. Pilots do not notice it, hikers do not notice it, but computers in orbit absolutely do. The region has a name that sounds like a footnote and behaves like a boss fight: the South Atlantic Anomaly. Picture Earth's field as a flowing dome. In most places, it presses back hard against space weather. Here, the dome dips. Spacecraft that skim through this corridor encounter more high-energy particles than their designers like. Detectors click faster. Camera sensors register bright specks as radiation punches through. Memory bits flip from 0 to 1 in silence. Operators call these events single-event upsets. One upset is a hiccup. Thousands over a mission lifetime become a maintenance plan. Engineers adapted. They schedule critical uploads outside, the corridor. They power down sensitive instruments before entry and power them back up afterward. They add shielding mass to protect parts that cannot fail. The International Space Station even changes orientation when practical, to let more robust surfaces face the particle stream during passage. None of this is panic. It is respect. Space is harsh everywhere and a little harsher here. Maps tell the longer story. 2 decades ago, the anomaly sat mostly over open ocean. Today, its footprint stretches inland, brushing Brazil and Angola and Namibia. The numbers vary by altitude and season, but the trend line is stubborn. In the last decade, analysts also watched a second weak cell emerge under Southwest Africa. Imagine an eddy spinning off the main river. That new pocket deepened faster than models expected, a hint that the flow beneath our feet is reworking pathways at the core mantle boundary. That boundary is where the metaphor earns its keep. The field you feel at the surface is the sum of structures born far below. Most of the time, the global dipole dominates like a strong current running downstream, but turbulent flow in the liquid outer core can twist some of those field lines back on themselves, creating reversed flux patches. These are local zones where the magnetic direction opposes the main field. They are not voids, they are counterflows. Put enough counterflows in one sector, and the surface strength there sags. The anomaly is what that looks like from space. Why here? Seismic images of the deep mantle show dense, hot structures under parts of Africa and the Pacific. They are not molten oceans, just slow regions where mantle rock differs from its surroundings. Differences in heat flow across the core mantle boundary can steer the convective patterns of the liquid iron below. Where heat escapes faster, flow can be more vigorous. Where it escapes more slowly, flow can stall or reorganize. The South Atlantic region sits above interesting deep mantle reel, estate, and the magnetic map appears to care. None of this means satellites are doomed. It does mean the margin between expected radiation dose and design tolerance is thinner over this patch, so operators act accordingly. It also means the anomaly is a laboratory for studying how local structures can drain energy from the global dipole and feed higher-order multipoles that do a worse job at shielding low Earth orbit. That is why particle physicists and space weather teams pay such close attention. The anomaly is both a hazard and a teacher. The tempo change is the unsettling part. Anomalies have waxed and waned across geological time. The South Atlantic Anomaly is not new in principle. What is new is the pace we can measure. Satellite generations are short. Mission managers plan in years, not millennia. When the footprint grows visibly from one mission to the next and a second minimum appears inside a decade, it sharpens the mood. We are watching a living system in motion on human time. Could this be the opening act of a polarity reversal? The rock record shows that reversals unfold slowly, compared to a career, and there have been many swings that start and then subside. The existence of a deepening anomaly does not guarantee a flip. It does guarantee better questions. How stable are the reversed flux patches feeding it? Are we seeing a transient rebalancing of core gyres, or the first phase of a longer restructuring? What do high-resolution time series say about the growth rate in different altitude bands? And how do those rates compare to model ensembles? There is also a public communication challenge. A plot with a falling line and a red blob that grows year by year is easy to misunderstand. The field is not collapsing across the whole planet. Your compass still works. Aircraft still navigate without drama. The concern is localized environment for spacecraft and the broader scientific puzzle of why this region in this decade. That is a fine distinction, but it is the truth. Alarm without context creates noise. Context creates agency. Here is the practical meaning. If you build hardware that will pass through this corridor, you design for more bit flips, more detector hits, and more time spent in safe mode. If you operate a mission already aloft, you adjust procedures and accept that this slice of sky is less forgiving. If you write models of the core, you treat the anomaly and its secondary minimum as hard constraints your equations must respect. If your curiosity asks whether an external visitor could be stirring the pot, you write down the mechanisms and their expected signatures, and you look for them. That is how a hot zone in near-Earth space becomes a clean test for ideas. We are going to follow those reversed flux patches back to their source, down where liquid metal moves like weather in slow motion, down where gyres can steal energy from the simple melody and tuck it into complicated side parts. If the anomaly is the surface, the symptom, the next stop is the engine room. Stand on the sea ice of the high Arctic with a good compass and a clear horizon, and you can feel how the world misbehaves. North is not a fixed star for magnets. The North Magnetic Pole is a moving target, and in our lifetime, it has stopped strolling and started to run. For centuries, it meandered around the Canadian Arctic archipelago. In the modern era, it has surged towards Siberia, covering tens of kilometers each year and dragging the geometry of navigation along with it. Why does a pole move at all? Because the field we live inside is the surface echo of deep flows. Down in the liquid outer core, slow rivers of molten iron organize into broad gyres. Above North America and above Siberia, two great lobes of magnetic strength tug at the pole like rival captains on a rope. For a long time, the Canadian lobe held the advantage. In recent decades, the Siberian lobe has grown stronger, while the Canadian lobe has weakened. The result is a decisive pull across the polar basin. Speed matters. Numbers on this story are not fireworks, but they reshape practice. When the pole's drift rose to roughly 50 to 60 kilometers per year, small errors in heading began to accumulate faster than the world had planned for. The global magnetic model that pilots, surveyors, and smartphone sensors rely on is refreshed on a rhythm of years. That rhythm had to bend. An unscheduled update landed to keep compasses honest in aviation cockpits and in apps that assume north means now. It was a quiet drama, felt first by professionals who watch error bars for a living. If you have ever looked at a runway number and wondered why airports sometimes repaint, here is one answer. Runway headings are rounded to the nearest 10 degrees of magnetic azimuth. When magnetic north shifts enough, the painted numbers need to keep faith with reality. That is not a crisis. It is housekeeping for a moving world. Polar route planners also care because near the top of the planet's satellite navigation can become finicky and magnetic references take on more weight. A few degrees of surprise in declination can tip a carefully balanced fuel plan or eat into reserves when winds are strong and alternates are far. The pole sprint is also a scientific clue. Poles do not choose a path. They are dragged by gradients in the field that are themselves created by flows at the core mantle boundary. The fast track towards Siberia tells us that the pattern of strong and weak regions under the Arctic is changing on human time. That observation does not tell us whether a reversal is brewing. It does tell us that the orchestra of multipoles under the simple dipole melody has shifted sections, pushing the apparent note across the staff. On maps, this story plays out as changing lines of equal declination. A hiker far from the poles may feel only a gentle nudge as the angle between true north and magnetic north drifts a little each year. A survey team near the Arctic Circle feels a larger slide and updates more often. Mariners and pilots in high latitudes live with it day to day. The fix is not mystical, You download the new model, recalibrate if the system asks, and carry on. The lesson is cultural. We live on a planet that moves in ways our grandparents were told to consider slow. Some of those motions have picked up the beat. There is a deeper human angle here. Compasses are story machines. They lean on a myth that north is a reliable friend you can point to. Watching the pole race eastward forces an emotional update. The map in your head gets a jolt and a little wonder leaks in. The Earth is not a static stage. It breathes and shifts in iron and stone. That recognition does not make travel riskier. It makes our relationship to measurement more honest. We do not own north. We negotiate with it. Could a distant visitor nudge this sprint? The physics says no, for the same reasons we will keep revisiting throughout our investigation. The energy available from a comet at a vast distance is tiny compared to the power in the core. The timescale of a flyby is brief compared to the years over which these flows build and strain. The drift began long before anyone put a provisional name to a faint point of light racing past the Sunday. This is a homegrown motion with roots in deep Earth weather. So, treat the pole's voyage as a living gauge of the engine room below. When the drift speeds up, the balance of subsurface forces is changing. When it slows down, the balance eases. When it kinks or jerks, something in the flow has snapped into a new pattern. Watching those moves and maintaining the maps that follow them is not just upkeep for navigation. It is how we listen to the core without drilling a meter. We have looked at the sag in the shield over the South Atlantic and at the running needle over the Arctic. Both are surface signatures of deep processes. Now we pivot from the planet to the passerby. The next chapter introduces the interstellar traveler, whose timing made all of this feel like a single story. It is not a threat. It is a gift with a clock on it. Out beyond the orbit of Earth, a faint speck slid across a star field and refused to behave like a local. Astronomers measured its path, did the math, and the curve would not close. That is the telltale of an interstellar guest. We call it 3I Atlas. It is only the third such visitor humanity has confirmed, after one that looked almost alien in its restraint and another that looked comfortingly comet-like. This one sits in the middle of the family portrait, harmless by geometry, fascinating by behavior, a messenger from a chemistry set we did not assemble. Discovery stories are detective work. Survey telescopes sweep the sky and catch motion against the background. Pre-discovery images sometimes hide in older data like clues in a drawer. In early July of this year, teams locked in an orbit that said hyperbolic. Translation for the rest of us. Gravity from the sun can bend this object's path but cannot capture it. The speed is above solar escape. 3I Atlas will fall inward, sweep past, and leave forever. At closest to the sun, it passes roughly 1 4/10 astronomical units. That is beyond the orbit of Earth, not inside it. Later in December, it comes nearest to Earth at about 1 8/10 astronomical units. That distance is so large that even the most anxious voice in your head can relax. So, why the spotlight? Because interstellar objects are time capsules. Imagine a small worldlet born around a star we will never visit, built from dust and ice in a disk with its own temperatures and ingredients. Something nudged it free ages ago, perhaps a migrating giant planet, perhaps a close stellar brush. It wandered the cold between suns for millions of years until random chance delivered it to our neighborhood. When sunlight finally warms that surface, ices sublimate. Gas drags dust away. A comet wakes up. In that coma and tail are fingerprints of a birthplace far from home. 3I Atlas comes alive early. Many comets nap until they are inside 3 astronomical units, where sunlight is strong. This one started breathing water vapor while it was still beyond that line. That early activity hints at either a crust rich in super volatile ices that kick off at lower heat, or a structure that allows heat to reach deeper seams more efficiently. Both options say other systems build different kinds of small bodies. Polarimetry adds another clue. When sunlight scatters off dust grains, the reflected light can line up in preferred directions. The pattern depends on grain size, shape, and composition. Observers logged a deeper negative branch than usual. That phrase simply means the dust does not match the average solar system recipe. It is fluffier or more porous, or built from materials that bend light in new ways. None of this changes the headline that matters to safety. The orbit does not cross ours. The mass of a small comet is trivial next to a planet. The magnetic and electric games in its ion tail are impressive in a telescope and microscopic at the scale of Earth space. What it offers instead is a clean experiment. Watch a comet from another star wake up around our Sunday, measure what it leaks and how the dust behaves. Compare the behavior to our homegrown comets. Use those differences to update models of planet formation in places we cannot see directly. Size estimates suggest a nucleus, perhaps in the range of 5 to 6 kilometers across. That is big for a short-period family comet and ordinary in the grand census. The surface is almost certainly dark, the way most cometary surfaces are, because sunlight bakes off brighter ices and leaves a crust mixed with complex organics and dust. Under that blanket are pockets that respond as the object rotates. One face turns toward the sun and jets. Hours later, a new region lights up. That's staggered. Breathing sculpts the tail into structures that can look lumpy and asymmetric in images. If the nucleus has weak spots, it may shed fragments near closest approach to the Sunday. If it holds together, activity may still spike as fresh ice is exposed. Either way, the event is physics, not omen. Interstellar context helps. The first visitor we found became famous for moving as if tiny thrusters were attached while showing no obvious dust. The likely answer was exotic ices that evaporated invisibly, or an unfamiliar geometry that hid the signs. The second visitor was blessedly normal. Gas, dust, classic spectra. That was a relief to modelers who wanted at least one clear example. 3I Atlas splits the difference. It is unambiguously a comet. It is also a touch weird. Early water emission beyond 3 astronomical units. Polarization curves that make dust specialists scribble in the margins. Enough odd to be memorable without tripping into myth. If you are a builder of missions, this is the kind of object that tempts you to dream about. Interceptors kept on standby. A small craft parked in a helpful orbit with high acceleration engines could sprint to meet a newly discovered interstellar target and taste the dust as it streams away. We are not there yet. Discovery came too close to perihelion for even the boldest crash program. But the idea is now in the air, and future surveys will give us more warning for the next one. 3I Atlas is a teacher in that indirect way. It says, hurry up. The galaxy is delivering opportunities and our response time is the true limiting factor. In the meantime, the ground game matters. Spectrographs will keep splitting the comet's light to read its chemical inventory. Polarimeters will keep tracing how dust twists that light. Photometry teams will watch the brightness rise and fall and will infer rotation rates and jet activity. Plasma monitors will watch the solar wind for any tail-related disturbances, not because danger lurks, but because the heliosphere is a laboratory and comets are stirring rods poked into its flow. Here is the most human part of the story. People around the world step outside after dinner, look up, and know that a rock from another star is in our sky, visible only through instruments yet as real as the ground under their feet. It is a shared sense of scale. The core under you is molten metal writing a magnetic song. The visitor above you is a freezer-burned memory of a different creation. Both are moving, both are honest. Both reward attention. That is why this episode pairs them. The timing may be coincidence, the wonder is not. Next, we follow the dust and the light a little further. We dig into the puzzles that make this comet scientifically rich and narratively irresistible, and we keep one eye on the distance that keeps us safe. The first odd note was a whisper of water, long before the sun should have had that much pull. Many comets hit the on switch inside 3 astronomical units. 3I Atlas started breathing farther out. That is not just a calendar quirk. It is a clue about chemistry and structure. Either the surface carries super volatile ices that wake at lower heat, or the crust is cracked and porous in a way that lets warmth travel faster and deeper than usual. In both cases, the object is telling us where and how it was made. Start with the possible culprits. Carbon monoxide and carbon dioxide ices sublimate in the cold and can drag water molecules with them. If 3I Atlas formed in a darker, colder nursery than most solar system comets, a richer mix of these super volatiles would make early activity natural. Another option is architectural. Imagine a sponge rather than a brick. Sunlight warms the skin, heat seeps inward through tunnels and pores. Buried ices feel the change and begin to lift off. As gas percolates back through that sponge, it carries dust grains into a growing coma. The same result can arrive through a third door as well. Amorphous ice can flip to a more ordered form and release latent heat while doing it. That little bonus can push a marginal region over the line. Now turn to the dust itself. When sunlight bounces off a cloud of grains, the scattered light can line up in preferred directions. Polarimetry is the art of measuring that alignment. Most solar system comets draw a familiar curve when you plot polarization against viewing angle. 3i Atlas bent that curve lower in the small angle region. In plain words, the dust is more efficient at flipping the orientation of light than our average templates predict. That tends to happen when grains are fluffy, porous, or built from a mix that changes how light travels inside them. Think fractal snowflakes rather than compact pebbles. The physics is subtle, yet the impression is simple. Different factory, different parts, activity that starts early, and dust that polarizes in a strange way point to formation beyond familiar frost lines. In the protoplanetary disk around another star, temperature and chemistry vary with distance. Farther out, ices that never condense here can build into bodies more easily. If that is where 3i Atlas learned its tricks, it carries the fingerprints of a colder pantry. Spectrographs will chase that thought with line-by-line inventories of water, carbon monoxide, hydrogen cyanide, and other tracer molecules. If we are lucky, future observations will pin down isotopic ratios such as deuterium to hydrogen in water. Those ratios are thermometers that stay honest for billions of years. The shape of the tail adds another layer. Comet dust feels sunlight push like a steady wind, so a broad dust tail sweeps away from the sunday. Charged atoms and molecules feel the magnetic fields carried by the solar wind, so a narrow ion tail points more directly downwind. When a nucleus rotates and jets turn on and off as different faces greet the sun, both tail systems get streaky and lopsided. Photometry, teams watch the light rise and fall to infer rotation periods and jet geometry. Early reports of asymmetric structures around 3i Atlas fit that story well. Lumps in the coma are not magic. They are time and spin made visible. Why should you care about the difference between a dust tail and an ion tail? Because they are live sensors for two environments at once. The dust tail is a history of the last few days of outgassing and rotation. The ion tail is a seismograph of the solar wind. Kinks and disconnections can mark changes in the wind that would otherwise pass silently. In that sense, a comet is a drifting probe that writes the local space weather into its own hair. Here is the elegance of the early activity puzzle. It takes fear off the table and replaces it with craft. We are not trying to survive this visitor. We are trying to read it. Every odd detail is a hook for a better model. Why did water switch on beyond 3 astronomical units? How deep do the pores go? How fluffy must the grains be to bend light that much? If the nucleus fragments near perihelion, do the fresh pieces carry the same polarimetric signature, or was the crust hiding a more ordinary interior? Each answer narrows the family tree of possible birthplaces. You can also feel the payoffs ripple outward. Planet formation models must allow for disks that produce objects like this at scale. Survey strategies must be tuned to spot early activity. Far from the Sunday Future Intercept missions must be ready to sample dust that is fragile and airy rather than compact and tough. Even simple things like image processing pipelines need to handle polarimetric quirks without forcing them into old templates. 3i Atlas is not just a comet, it is an update request to a dozen playbooks. There is another human angle here as well. Early activity means the show lasts longer, more nights to watch the graphs creep, more mornings to check whether a jet swung into view, more chances for Citizen, to scientists to contribute real measurements from small telescopes that can monitor brightness and morphology, while big instruments chase spectra and polarization. A long runway turns a curiosity into a community project, and that is how science scales beyond the walls of a single observatory. So, the puzzle sharpens. An interstellar traveler wakes early and scatters light in a way that betrays fluffy grains from a colder workshop. It spins and jets, and writes the solar wind into its ion tail. It remains safely distant, yet it keeps handing us new ways to learn. Next, we step back and ask a broader question. When anomalies pile up, how do we separate the few that will survive scrutiny from the many that will fade with better data? Anomaly is a tempting word. It tastes like secret and revelation at once. The truth is more ordinary and more useful. When you measure many things with sensitive tools, some will look odd just by chance. If you flip enough coins, you will eventually see 10 heads in a row. That streak does not mean a new coin law has been discovered. It means you did a lot of flips. 3i Atlas gives us many flips. So does a global magnetic field mapped from space. The trick is, turning spectacle into signal without letting noise dress up as news. Start with a simple checklist that any curious mind can carry. First question: does the odd feature appear in independent datasets that were processed by different teams? If a strange light curve bump shows up in one telescope but not in another that watched at the same time, odds are you caught an instrument twitch. If a weak spot in the magnetic map shows in satellites and in ground stations, confidence rises. Agreement across methods is stronger than beauty in a single plot. Second question: does the anomaly persist when you change the rules? Analysts call this robustness. You vary the time window, you use a different background subtraction, you change how you filter out solar activity. A real feature tends to survive gentle abuse. A mirage tends to fade when you poke it. Good teams publish sensitivity tests so that others can repeat them. That habit is not bureaucracy. It is how we keep from falling in love with the first story that flatters us. Third question: is anyone making a prediction that could be wrong in public before the next data arrives? This is the cleanest way to separate a pattern that seemed obvious after the fact from a real relationship in the world. A magnetospheric model that says a kink should appear in a comet's ion tail on a specific date if a certain solar wind geometry holds can be tested. A core flow model that projects the South Atlantic weak cell will deepen by a defined amount by next year can be tested. The calendar becomes a referee that does not care about our excitement. Fourth question: are you counting the number of shots you took? This is the look elsewhere effect in plain clothes. If you scan 100 parameters and celebrate when one crosses a threshold, you must remember you peaked at 99 others. The honest fix is to report the full search and then ask the community to confirm the hit with fresh data. If the signal was real, it will come back when called. If not, it will retire quietly to the land of neat plots that did not survive. Fifth question: does the anomaly scale the way the proposed mechanism says it should? Physics loves proportionality. If you claim a comet's dust jets cause a certain tail twist, then doubling the jet strength ought to double the twist within some tolerance. If you claim deep mantle heat flow patterns are feeding reversed flux patches, then regions with similar mantle structures should show similar magnetic behavior down the line. When magnitude follows logic, narratives harden into models. When magnitude floats free of logic, you are probably looking at an accident. This is the lab mindset we want to model together on camera. Wonder is welcome, so is restraint. When a report mentions 8 curious features in 3i Atlas, we do not treat 8 as a score to beat. We treat it as a to-do list. Each item enters the ring against the 5 questions. Early water at long distance passes the first test because several instruments saw it. Polarization curves that bend lower than expected pass the second because they persist across nights and calibrations. Alignment angles that look improbable fail the fourth because the search space was broad and the counting was sloppy. That is not dismissal. That is triage. The same playbook keeps us honest on Earth. The South Atlantic Anomaly is not an anecdote. It is repeated by satellites with different orbits and different sensors. It survives robustness checks under different solar conditions. It lands predictions that engineers can act on. Memory upsets go up inside its borders and go down outside. The secondary minimum under Southwest Africa emerged in independent pipelines. That is why it sits in the must explain column, rather than the neat if true column. There is also a cultural piece here that matters to a long investigation. Open data is not a slogan. It is a way to get more eyes on hard problems and to diffuse the drama that secrecy breeds. When orbit solutions for an interstellar object update, the files are there for anyone to compare. When field models bump mid-cycle, the coefficients and the residual errors are posted. That transparency lets the audience turn from personality to process. It also creates a fair game for dissent. If a team thinks the subtraction of external fields is hiding a core signal, they can prove it by reprocessing the same inputs and showing the improvement. One more habit worth adopting. Keep a short list of would change my mind signals in your pocket. For the comet, that might be a repeatable tail disturbance that tracks the object's position over months with a lag pattern a model can predict. For the core, that might be a phase-locked response in deep field harmonics to a multi-year external driver. These examples are not likely, they are clear. Clarity is what protects curiosity from both hype and cynicism. When anomalies pile up, the right response is not to cheer or jeer, it is to build lanes that only real signals can drive through, replication across tools, robustness under stress, predictions on the record. Honest counting of shots, scaling that matches mechanism. Do that 5-step dance often enough, and the occasional coin streak that is truly special will reveal itself. The rest will melt into the background where it belongs. We now have our filter. Next, we put the mainstream case on the table with equal clarity. Energy, distance, time. Why physics says the comet and the core are ships in the same night, passing without a whisper. Start with the blunt accounting. A small comet, even a dramatic interstellar one, weighs almost nothing compared to a planet. Earth carries roughly 6 times 10 to the 24 kilograms of mass. A typical comet nucleus carries trillions of kilograms. That difference is not poetic, it is decisive. Gravity from such a small body at a distance of hundreds of millions of kilometers is a whisper during a thunderstorm. Tides from the moon and the sun already tug on Earth far harder than any comet ever will, and those familiar tides do not rearrange the iron ocean at the core in ways that show up in the field on human time. Now, add the insulation problem. Between space and the dynamo is a thick shell of rock and mantle roughly 3,000 kilometers deep. Electric fields and magnetic wiggles from above lose their strength as they try to penetrate that shell. Currents in the ionosphere and magnetosphere can and do induce little currents in the ground. Power grids feel those during big solar storms. The trick is that those induced currents fade with depth long before they can touch the engine room. The core is not just far, it is shielded by physics. Timescales seal the case. Space weather breathes in bursts of minutes to days. The geodynamo evolves on years to centuries, and flips in polarity sprawl across thousands of years. You cannot nudge a centuries-long river with a gust that lasts an afternoon, and then claim that it turned the delta. The known changes in Earth's magnetic field, from the long decline in dipole strength since the 1840s to the recent spread of the South Atlantic Anomaly, began well before the first images of 3I Atlas. The timing that feels uncanny in a headline looks ordinary on a calendar that runs decades long. Models back this up. The global maps that pilots, phones, and drill rigs rely on are built from a language that resolves the field into simple and smaller scale parts. Those maps are updated on a steady rhythm, and sometimes out of rhythm when the world moves faster than expected. None of those models require knobs for comets or distant plasma tails. They fit the data by adjusting the internal melody and its harmonies. When the North Magnetic Pole sprinted towards Siberia, the fix was to update the internal picture, not to add a new external driver. Energy budget is where many beautiful stories go to die. The magnetic energy stored in the core and the mechanical energy in its flows are immense. To change the tune down there, you either add comparable energy or you tweak the boundaries in a way that leverages what is already stored. A comet cannot add the first. Its gravity is laughably small on that scale. Its plasma tail, even if impressive in a photograph, carries tiny electromagnetic energy compared to the flows within Earth. Could it tweak a boundary? That is where speculation lives, and even there the numbers shrink to nothing long before they matter. What about resonance? Could a small signal at just the right frequency whisper to a mode in the core and grow? Resonance is a fair question in physics. It is also picky. You need a sustained signal that matches a natural rhythm, and a clean path for that rhythm to reach the system you want to stir. The comet's presence is brief at perihelion, and the tail is a moving, diffusing thing carried by the solar wind. The rhythms we see in the core, such as slow torsional oscillations, play in years and decades. The chance alignment needed for a resonant handshake is vanishing, and the coupling path still has to cross the same insulating mantle. Another mainstream point lands softly but firmly. The field's current behavior has family resemblance to past behavior recorded in rocks and sediments. The planet has wandered, weakened, and sometimes flipped many times across deep history with no help from visiting ice and dust. The South Atlantic Anomaly is unusual in its pace on our watch, but anomalies and regional weak spots are not new to the magnetic record. When a pattern fits the known habits of an old system, we do not need to import a guest star to explain it. There is also a humility baked into the no-link verdict. Scientists who study the core are the first to admit what is hard. We do not see the flows directly. We infer them from the field at the surface. We know the equations. We cannot solve them at full fidelity for the whole core for long stretches of time. Uncertainty here does not open a door to anything goes. It sharpens the standard for alternative proposals. If you want to connect a comet to core dynamics, show the pathway, show the power, show the timing, and show the prediction that could fail in public. Until then, the simpler picture wins. None of this kills curiosity, it cleans the workbench. With the wild claims swept aside, we can look for real, testable ways external environments influence near-Earth space, and we can keep asking whether internal boundaries are evolving in ways that explain the present tempo. We can enjoy the coincidence without mistaking it for a clue. The comet remains a gift for understanding other solar systems. The magnetic field remains a grand and restless system that does not need a visitor to surprise us. Hold both truths at once. The universe is allowed to produce a striking alignment that means nothing beyond narrative symmetry. Physics asks for mechanisms and magnitudes that meet the bar. Here, they do not. We will keep checking because that is how you keep trust with an audience and with the world. But the honest baseline is decisive. Earth's changing field is a homegrown story, and 3i Atlas is a harmless traveler whose best trick is teaching us about faraway nurseries of ice and dust. With the mainstream case set, we can play a useful mental game. What would it take, in principle, for small nudges to matter in a twitchy system? That thought experiment is not permission to believe. It is training to test better. Next, we visit thresholds and tipping stories in the core, where tiny shifts at the right time can loom larger than they should. Picture a marble balanced on the ridge between two valleys. A tiny tap decides which slope it chooses, yet most of the energy in the ride comes from gravity that was stored all along. That image is what scientists mean by a threshold. The push does not power the fall. It sets the direction when the system is perched at a sensitive point. If Earth's core ever sits near such a ridge, small changes at the boundaries could matter more than their size would suggest. Now translate the marble into molten iron. The outer core is a deep ocean of conducting metal in motion, organized by rotation into broad helical flows we can think of as gyres. Those gyres stretch and twist magnetic field lines, feeding the simple global dipole that makes compasses work. But flows compete. When a gyre feeds energy into smaller, more tangled structures, the dipole can weaken even while total magnetic energy stays high. That is the orchestra metaphor in metal form. The melody thins while the side parts grow loud. Reversed flux patches are the local fingerprints of that, reshuffling. They are zones at the core mantle boundary where field lines loop the wrong way compared to the global dipole. At the surface, stacked above those patches, the field sags and complicates. That looks like the South Atlantic Anomaly and its offspring under Southwest Africa. If those patches strengthen or multiply, the surface shield over that region fades and satellites feel it first. The planet has not turned off its magnet, it has reallocated power. Why would thresholds appear in such a large, hot system? Because even giants have sensitivities when the geometry of flow and the shape of the boundaries line up just so. Heat leaves the core unevenly because the mantle above it is not uniform. Some regions steal heat fast. Some regions act like a blanket. That patchwork can help set up rival gyres, each trying to claim energy. If the balance hovers near even, a small tweak in boundary flow could tip the contest. The marble rolls not because the push was big, but because the decision was close. There are hints that the field has been in an active mood. The anomaly footprint grew faster in the last decade. The North Magnetic Pole sprinted towards Siberia and forced an unscheduled map fix. Short, sharp kinks in the records called jerks show that parts of the system can change their pace on the scale of months to years. None of this proves a threshold, but it paints a picture of a machine that is not idling. When motion quickens, sensitivity often rises. If thresholds are real, they leave evidence. Systems near a tipping point can show critical slowing down, which is a fancy way of saying they take longer to recover from a nudge. Variability can increase as the system wobbles between competing states. Correlations across different parts of the system can tighten because one slow mode starts to dominate. In practice, we would look for patterns like those in the time series of the field's smaller scale components and in the drift of the pole. We would check whether anomalies relax more slowly after external space weather pulses than they used to, even if space weather is not the driver. A threshold story is tempting because it gives small signals a possible role without violating energy budgets. The role is not to power change, but to choose pathways among changes already poised to happen. It is the difference between pouring fuel on a fire and opening a door for a wind that is already blowing. That framing keeps us honest. It invites tests rather than tales. It also respects the mainstream point that core dynamics carry the load. What would it take to upgrade this from a neat analogy to a working model? First, we need clear diagnostics that separate threshold behavior from ordinary turbulence. That means precise, long-duration monitoring of the higher-order harmonics in the field and careful attention to jerks and recovery times. Second, we need models that can produce both regimes under small boundary shifts. If a change in assumed heat flow at the boundary moves a simulation from a strong dipole to a weaker, more multipolar state, and does so with the same kinds of surface signatures we observe, confidence climbs. There is room for humility here. The equations that govern the geodynamo are known and unforgiving. We can write them. We cannot solve them at full fidelity for centuries of evolution with today's computers. That gap means we lean on reduced models and on data-driven methods to bridge distance between theory and observation. Thresholds can hide inside that gap. They are also the first casualties of sloppy thinking. Every noisy curve can be dressed up as a tipping point if you squint hard enough. The cure is discipline and pre-registered predictions that live or die in public. If the core is hovering near a ridge, what kinds of boundary nudges could matter? The honest answers are internal. Variations in heat flow driven by slow mantle circulation. Changes in composition at the inner core boundary, as it crystallizes and releases light elements. Long-term modulation from the history of plate motions that shuffle continents and alter how heat escapes through the mantle. Each is a lever rooted in geology, not in passing visitors. That does not forbid tiny roles for external rhythms. It simply puts them in the right order of plausibility. Here is the useful takeaway. Threshold thinking gives us a way to ask better questions without leaping to exotic causes. It tells us what to watch in the data and what patterns would elevate a hypothesis. It also gives us a stage on which to test external ideas fairly. If a coupling pathway from near-Earth space to the mantle to the core exists, could it act as a phase hint to a system already near a decision? The default answer remains no for both physics and scale. The scientific answer is, show me, which is exactly what we will do next. We will trace the cleanest imaginable external pathway step by step, from the magnetosphere down through the ionosphere to the ground, and measure how quickly the signal dies. If thresholds could save a weak link, this is where they would try. Then we will see whether any of that survives the numbers. Begin at the top of the sky, where the sun's wind meets our shield. The solar wind presses on Earth's magnetic field and reshapes it every minute. On the day side, the shield is squashed inward. On the night side, it stretches into a long tail. When the wind's magnetic field happens to link with Earth's field, energy pours in. Currents race along magnetic lines toward the polar atmosphere and close through vast loops called auroral electrojets. The lights are beautiful. The physics is louder than fireworks. Those loops do more than glow. They change magnetic fields on timescales of seconds to hours. Changing fields induce electric fields. That induction reaches down through the thin air of the ionosphere into the rocks below. During a strong storm, slow ripples of electric potential creep through the ground over hundreds of kilometers. Power grids act like antennas. Pipelines feel unwanted, direct currents. Operators watch gauges, shift loading, and ride out the storm. This is the cleanest example of space weather touching human infrastructure on Earth itself. So could the same induction touch the core? Trace the path carefully. From magnetosphere to ionosphere, the coupling is strong. From ionosphere to ground, the coupling is real yet already weaker. From crust to mantle, it weakens again. Electrical conductivity rises with depth in some layers, which helps fields penetrate, but the signal still fades because time matters. Slow variations reach deeper than fast ones. Storm time wiggles are quick. Quick signals die shallow. Engineers describe this with a skin depth idea. You can picture it without math. Imagine trying to shout through a thick wall. A slow, low drum beat carries a little farther than a high-pitched chirp, but both fade fast. For induction from above, the drum beat equals changes that unfold over days and longer. Space weather's main rhythms are minutes to hours. The wall is 3,000 kilometers thick. Most of the shout is gone long before the sound would reach the engine room. Could extended, gentle forcing matter more than a short blast? Suppose the magnetosphere stayed slightly reconfigured for weeks. The ionosphere would carry persistent currents. The ground would feel a low, steady nudge. That picture is friendlier to depth than a single burst, yet the numbers are still small. The magnetic energy density in the core is immense. The induced fields from above are tiny by comparison, and they are noisy, not clean tones that line up with a natural beat in the core. That brings us to resonance. If the core has slow oscillations that repeat over years, could a weak but steady external rhythm tickle them? Maybe in a fairy tale where frequencies match and a stable phase hold is possible. In the real sky, the solar wind changes mood constantly. Even quiet periods wander. A comet's plasma wake is weaker still and rides inside that restless wind. Matching a multi-year core mode with a fuzzy, drifting driver would be like trying to push a playground swing with random taps while blindfolded and standing in a crowd. Sometimes the swing moves, but you do not get credit. There is a second hurdle. Even if a small part of the external signal slipped deep, the core would answer mostly in its own voice. The geodynamo is self-excited. It maintains the field by turning kinetic energy of flow into magnetic energy. A faint outside whisper would have to couple into that loop strongly enough to change where the energy goes. That means adjusting how gyres steer field lines at the core mantle boundary. We can test for that. If magnetospheric indices ever phase lock with specific features of the secular variation over many cycles, with lags that make physical sense, that would be a clue. So far, long records of the field do not show that kind of handshake. This does not make the space weather story boring, it makes it precise. The magnetosphere and ionosphere are powerful partners that drive auroras, heat the upper atmosphere, and create ground currents that can stress grids and submarines. They can change the boundaries that satellites feel from one orbit to the next. They can even change how much solar radiation reaches hardware inside the South Atlantic Anomaly. Those are real levers with practical playbooks. They also give us instruments. If you want to look for fantasy couplings, you monitor the whole chain at once. Magnetometers in space map the wind and its field. Radar and radio sounders track ionospheric currents and densities. Ground arrays measure induced electric fields over rock types with known conductivity. Deep Earth teams watch the slow harmonics of the field. If an external signal ever mattered to the core, you would expect a repeatable pattern that connects these layers in order, with a clear time delay and a consistent sign. There is a final useful turn. Even when the answer is almost surely no, mapping the pathway teaches us where yes lives. Yes lives in satellites and station electronics that need protection during storms. Yes lives in airline routing at high latitudes during radiation events. Yes lives in power grid operations and in pipeline corrosion management. And yes lives in the simple delight of seeing curtains of green and red dance across a dark sky while knowing the circuits of Earth and Sun that power them. Space weather is a force we respect. The core is an engine we revere. Between them stands a thick, stubborn planet that keeps most short-term sky signals from reaching its heart. That is not a disappointment. It is a relief. It means we can study the magnetosphere as weather and the core as climate, each on its own tempo, without mixing their stories except where the physics allows. Next, we use that clarity to chase a narrower question. If a comet is essentially a moving plasma experiment, what does its tail really do to the wind around it, and what can that teach us about the space our satellites inhabit? Think of a comet as a moving chemistry lab with its own windsock. Sunlight warms the nucleus, ices lift off as gas. Ultraviolet from the sun strips electrons and turns some of that gas into ions. The solar wind then grabs those ions and drags them away from the sunday. That drag builds a long, narrow ion tail that points down the wind. Dust feels sunlight as a steady push and creates a wider curved tail. Two signatures, two clocks, two ways to read what is happening in space. The ion tail matters for plasma physics because it is not just paint in the sky. It is a disturbance that the solar wind must flow around. Picture a shallow river meeting a bundle of reeds. A small wake forms downstream. In the wind, the same idea becomes a magnetic wake, with waves and ripples launched into the flow. Spacecraft have flown through wakes of bright comets at a few tens of millions of kilometers from the nucleus, and have measured kinks in the magnetic field and bursts of new ion species. Those encounters are real lessons in how the wind responds to local injections of mass and charge. Now, place 3I Atlas on that stage. Its distance at closest approach to Earth is roughly 1 8/10 astronomical units. That is hundreds of millions of kilometers. The ion tail can be long on a human scale, yet even the grandest tails fade into background long before they can reach across that gulf in a coherent sheet. The solar wind is not a glassy stream. It is a choppy flow with turbulence that shreds and mixes fine structures. Material from the tail will spread into the wind and dilute. By the time any trace meanders near Earth, it is a whisper buried under louder voices from the sun itself. This is the key to mood. At Earth, the geometry is safe. There is no direct crossing of the core of the tail. There is no dense plume aimed our way. What remains is a clean chance to study physics without worry. Instruments near Earth can look for subtle shifts in ion composition that match molecules traced to the comet. They can look for slight changes in wave activity in the wind and see whether any pattern lines up with simple models of diffusion and advection. The expected answer is almost nothing. That answer still sharpens our tools. A comet also teaches by contrast. When the wind is calm, a tail can look like a straight sword. When the wind flips its magnetic field or launches a shock, the tail can kink or even appear to snap and regrow. Ground-based cameras capture those changes as sudden bends or disconnections. At the same time, spacecraft scattered through the inner solar system record the wind that caused the move. Match the bend to the gust and you get a 2-point lesson in cause and effect that helps validate space weather models. Distance also protects us from a common misunderstanding. Photographs compress scale. A tail that spans the sky in a long exposure is still thin in the measure that matters for interaction with Earth. It is a filament in a vast flow. The energy stored in that filament is tiny compared to the energy in the global magnetic environment that surrounds our planet. This is why we can enjoy the drama with no risk. The spectacle is for the eye and for the equations that describe a local experiment in a huge river. If you like checklists, here is what a smart observing campaign does with a distant comet. Spectrographs look for ions that act as markers for the tail. Magnetometers look for wave packets or rotations that pass the right region at the right time. Radio instruments watch for small changes in how signals scatter when they pass through wind that has been gently stirred. All of that lives in the land of small effects and almosts. That is fine. Small effects are where you train a field, to be honest. There is also a gift to operations. Even a faint wake can remind satellite teams how the wind changes drag on spacecraft and how ion composition tweaks charging on surfaces. The comet does not create those concerns. It lets us rehearse with a natural probe. If a tail feature shows up in data from a spacecraft well inside the orbit of Earth, analysts can test their pipelines and then look outward with confidence when larger drivers arrive from the Sunday. So the distant story is not a letdown. It is an invitation to precision. 3i Atlas is a silent stir stick in a giant stream far from our shores. We can watch how the stream reacts, collect a few grains of knowledge about ions and waves, and then fold those grains back into the models that protect hardware and explain the sky. The comet remains harmless. The plasma remains lively. The lesson remains worth taking. Next, we step out of the lab and into the rumor mill. When timing looks too perfect and updates take time, speculation rushes in. We will meet those stories with empathy and a sharper blade and show how to keep the signal high while the noise tries its best. Humans are storytelling machines. When two big events line up in time, our pattern-hungry brains reach for plot. A weakening shield overhead and a visitor from another star arriving the same year feels like a setup. That feeling is real and it is powerful. It is also not evidence. The cure is not to shame curiosity. The cure is to give it better tools so it can separate a good yarn from a good result without losing the thrill of the chase. Begin with empathy. People fill silence with stories because they care. They want answers fast and they want them to fit. If an agency goes quiet while teams process data, that pause can look like a cover-up. In reality, analysis takes time, calibrations drift. Pipelines need cross-checks. Releasing half-baked numbers burns trust. Waiting a beat builds it. The short-term pain is worth the long-term clarity. That is hard to believe. In a news cycle that never sleeps, so we narrate the waiting as part of the work, not as a gap that others should fill with smoke. Orbit updates spark a similar cycle. After discovery, a new interstellar object gathers more observations each night. With every added point, the best fit path tightens and shifts. To an untrained eye, the changing ephemeris looks like a secret push. To a dynamicist, it looks like convergence. The math improves as the dataset grows. The right response is not scandal. The right response is a smile and a reminder that good curves move before they settle. Anti-tails are another favourite misread. Sometimes a comet appears to have a tail that points toward the Sunday. That sounds like engine burn until you learn the geometry. Dust spreads out in a thin sheet along the orbital plane. When the viewing angle swings just right, we look edge on through that sheet, and it stacks into a narrow spear that seems to aim forward. As Earth moves, the spear fades, and the normal, tail look returns. No thrusters, just perspective playing tricks in a sky with depth. Open data is the quiet hero that lowers the temperature on all of this. Magnetometer readings from orbit are posted with documentation. Ground observatory logs are shared. Orbit solutions and their uncertainties are public. If someone thinks a result is off, the remedy is not a thread with ominous music. The remedy is a reanalysis with the same inputs and better methods, then a comparison in plain sight. Process beats personality, because process leaves tracks anyone can follow. Here is a pocket guide you can use the next time a wild claim tries to hijack your feed. Ask whether independent teams using independent tools see the same feature. If yes, interest goes up. If not, odds are you are looking at an instrument quirk. Ask whether the pattern survives small changes in method. Real signals tend to be robust under gentle abuse. Ask whether someone made a prediction before the new data arrived and then lived with the outcome. After the fact, explanations are easy. Before the fact, bets build trust. Ask whether the search counted how many shots it took. If a team scans 100 angles and only reports the one that looks spooky, that is fishing, not finding. Ask whether the size of the claimed effect scales the way the proposed mechanism says it should. When magnitude follows logic, belief grows. When magnitude floats, belief should not. There is also a language tweak that helps. Swap the phrase "they said nothing" for the phrase "they are still checking." Swap "we do not know" for "we do not know yet." Both keep the door open for real updates while turning down the heat. Curiosity does not have to sprint ahead of evidence to feel alive. In fact, it feels better when it paces itself to the rhythm of measurements. The magnetism story rewards that pace. The South Atlantic Anomaly grew on multiple maps and bit satellites in predictable ways. The pole sprint showed up in compasses, in flight, planning, and in a mid-cycle model patch. Those are bodies of fact that repeat under independent eyes. The comet story rewards the same calm. Early water at long distance turned up in multiple instruments. Polarization curves bent low across nights and calibrations. The safe distance stayed safe as more data flowed in. None of this needed a secret lever to explain it. The world is interesting at face value. What about the urge to connect the two stories anyway? It is fine to hold the question in your head as a spark for better tests. It is not fine to skip the tests because the timing feels too perfect. Physics has no respect for our appetite for symmetry. If a link exists, it will leave footprints across data layers in the right order, with the right delays. If it does not, the footprints will wander or vanish. We follow the prints, not the vibe. There is one more move that keeps a community healthy. Celebrate clean debunks. When a predicted tail kink fails to arrive, say so with the same energy you would give a hit. When a supposed drift in the field turns out to be a software bug, pin the bug to the board and thank the person who found it. That culture makes it safe to try, safe to be wrong, and safe to learn in public. It also makes it harder for bad actors to farm outrage for clicks, because the audience becomes fluent in how real discovery looks and feels. We are not trying to drain mystery from the sky. We are trying to keep mystery honest, so that when the rare thing happens, we notice it for the right reasons. That is how wonder survives the grind of evidence. It also prepares us for a wider stage where magnetic fields misbehave in many places, not just on Earth. The next stop is a tour through those other worlds, where surprises are normal and where comparison sharpens every question we ask at home. To understand our own shield, it helps to visit others. The solar system is a gallery of magnetic personalities. Some worlds roar with their own dynamos. Some borrow a field from a neighbor. Some sail naked through the wind and pay the price. Comparison strips away Earth bias and gives us a wider language for what magnetic fields can do. Start with the giant that owns the neighborhood. Jupiter's magnetic field is a cathedral. It dwarfs every other magnet in the family and carves out a cavity in the solar wind so large that the sun could fit inside it. Inside that bubble, moons live inside weather made of charged particles. One moon volcans like a fire hose and sprays material that becomes trapped in the field. Another hides a saltwater ocean under ice and answers Jupiter's changing field with its own induced currents. A third is the only moon known to run a dynamo of its own. Each tells a different story about how magnetism and interiors talk. Ganymede is the little dynamo that could. Beneath its ice and rock sits a metallic core that is warm enough and liquid enough to convect. Convection plus rotation plus conductivity makes a field. Spacecraft flying past have measured that field directly. It is weak compared to Earth's, yet strong enough to carve a pocket inside Jupiter's magnetosphere. That pocket creates mini auroras where lines from Ganymede connect into Jupiter's larger system. The lesson is simple and bold. You do not need an Earth-sized planet to make a field. You need a liquid metal layer, a source of buoyancy, and time. Europa plays a different tune. It does not have a hot metallic core running a dynamo. It has a deep, salty ocean that conducts electricity. As Jupiter's field sweeps past and changes direction, it induces currents in that ocean. Those currents generate a secondary field that spacecraft can detect. By reading that answer, scientists infer the depth and salinity of the ocean, and even hints about the thickness of the ice above. The lesson here is that magnetism can also be a probe. External fields shake a conductor, and the reply carries interior maps. Mars and the Moon tell the cautionary tale. Both once had stronger fields in deep time. Today they have patchwork fossils frozen into crustal rocks rather than a global shield. Without an active dynamo, solar wind strips away atmosphere over eons. Mars still has air, yet thin enough that liquid water hates the surface. The lesson is patience. Magnetic protection is not required for life in a moment. It matters across long epochs where the wind can grind a sky down grain by grain. Now, fold those lessons back into Earth. Ganymede says small bodies can have fast moods and complex feedbacks, even with gentle energy budgets. That reminds us to expect surprises from dynamo physics. Europa shows that induced fields reveal layers we cannot drill, which motivates better use of induction methods on Earth to study conductivity in the mantle. Mars shows what happens when the music stops, which frames our urgency to understand long-term stability as a practical question, not a trivia night fact. Missions sharpen this comparison. A polar orbiter that threaded Jupiter's radiation belts has skimmed close to Ganymede and Europa and tasted their fields directly. Instruments mapped how currents close, how the wind bangs on the door, and how moons reply. In the next decade, a European craft will settle into orbit around Ganymede and watch its field breathe over years. An American craft will fly Europa again and again and read the ocean's answer with fresh precision. Those time series will reveal whether small body fields change on short cycles and whether induced replies vary with geography and season. What would count as a surprise big enough to change our thinking about Earth? If Ganymede's field fluctuates on month-to-year scales beyond what simple models allow, it would tell us that boundary quirks can matter more than we guessed, even in small cores. If Europa's induced answer shows strong regional differences that demand exotic chemistry or layered oceans, it would remind us that conductivity profiles matter and that our own mantle may have more structure relevant to electromagnetic coupling than we assume. If a moon without a core field shows a persistent, unexplained magnetic feature tied to surface or ocean processes, it would stretch the playbook of how fields can be made or faked. There is also the way magnetism shapes habitability beyond shielding. Strong fields funnel particles and energy into atmospheres and surfaces. Aurora-driven chemistry can alter upper air in ways that trickle downward. Currents heat plasma and change winds. On moons with oceans, that energy may matter to ice shell dynamics. On exoplanets parked close to active stars, magnetic coupling can supercharge atmospheric heating. Each piece filters back to the question we care about at home. How do boundaries and feedbacks make big systems sensitive? The wider tour lands on a calming point. Earth is not uniquely on the brink because its field is lively. Magnetic fields across the system are lively by nature. They hiccup, surge, and sometimes stall. They answer to interior heat and composition, to rotation, and to the shape of the layers above and below. Our job is to replace static diagrams with living portraits and to accept that motion is the norm. That acceptance keeps us curious without defaulting to alarm. So the next time a plot shows a bend in our field or a bright visitor rolls through the inner system, remember Ganymede's pocket magnetosphere inside a giant. Remember Europa's ocean answering a celestial metronome. Remember Mars's quiet sky shaped by loss. Those memories make Earth's story larger and our questions sharper. They also set the stage for a jump beyond our system, where new telescopes have started to find atmospheres and magnets behaving in ways models did not expect. That is where we go next. We step into the exoplanet sky, look at worlds that run hot and fast, and ask how magnetism there might teach us something here. Point A, great eye into the dark, and it starts sending back weather reports from worlds you will never walk. Some of those reports make no sense at first. A giant planet skimming its star every few days shows grains of rock floating in the upper air. Another, still hot from youth, brightens and dims over hours as if storms the size of continents are rolling through. These are not rumors, they are spectra and light curves, and they are telling us that atmospheres and magnetism play together in ways our models did not predict. Take the hot giants that hug their stars. Daysides glow at thousands of degrees, while nightsides can be hundreds of degrees cooler. Winds scream from day to night, trying and failing to balance the heat. Instruments read the starlight that filters through the air during transit and find fingerprints of molecules that should not be abundant at those temperatures. Silicate vapor, metallic species, aluminum oxide. One explanation is volcanic delivery from beneath, supercharged by tides that need the interior. Another is patchy heating from above, where particles funneled by a magnetic field dump energy into the upper layers and cook chemistry in local hotspots. That second idea sounds exotic until you remember auroras at home. Earth carries currents that heat the thin air near the poles and change its chemistry. Scale that up for a planet pressed close to an active star, and you get an upper atmosphere that is not just warmed by light, it is electrified by charged particles. The signature would be temperature inversions and odd molecules where radiative models alone predict calmer air. Some hot giants show exactly that. It is not proof that magnetism is driving the stove, yet it is a clean clue that coupling matters. Direct images add a time dimension. Young giants far from their stars glow with leftover heat and can be photographed as dots. Watch those dots over many nights, and some flicker in infrared by amounts too large for smooth. Circulation to explain. Patchy clouds are one answer, uneven metallic hazes are another. A third is magnetically guided energy flows that carve hot lanes through the upper atmosphere. If the period of the brightness swings matches a measured rotation rate, we get a clock. If the pattern drifts slowly over months, we glimpse weather that evolves on human time rather than geological time. Why is this our business while we talk about Earth and a visitor with a tail? Because these surprises drill the same lesson into our heads. Boundaries and couplings change the game. A field that funnels energy from a stellar wind into an atmosphere can reshape temperature and chemistry without violating energy budgets. An ocean of conducting fluid inside a small body can run a dynamo and make a pocket magnetosphere. An induced field in a salty sea can reply to an external beat and tell you what lies under the ice. The list keeps growing. Every time a telescope forces a model to upgrade, we learn to be careful about what we call impossible. There is also a method gift. Spectral retrieval on exoplanets is a brutal test of inference. You start with a weak signal and peel away instrument quirks and stellar noise to get at real molecules and temperatures. Then you ask whether the inferred profile is unique. Often it is not. Multiple combinations of chemistry and haze and circulation can fit the same data. The cure is more data at more wavelengths and smarter priors that include physics we were tempted to ignore. That playbook transfers to geomagnetism. When different flow maps at the core mantle boundary explain the same surface field, we need longer time series, better constraints on mantle properties, and priors that admit multipolar mischief. Exoplanet results also change stakes for habitability. A strong magnetic field near a flaring star might protect an atmosphere by deflecting wind, or it might channel energy so efficiently that it strips the air faster. The answer depends on geometry and chemistry and time. That sounds familiar. Our field protects and sometimes exposes. Our anomaly creates a local hazard for satellites, while the ground feels little. Strength alone is not the full story. Configuration and context decide outcomes. Where does this leave our investigation? With humility and sharper questions. If telescopes can find rock vapor where simple thermometers said no, then we should expect Earth's core to throw us patterns our first-pass models miss. If young giants flicker on our scales, then it is not audacious to think that small components of our field can jerk on year scales. If magnetism can move energy around in alien skies, then we should look harder at how boundary conditions at home move energy between the dipole and the side parts. None of this rescues a comet core link. It strengthens the baseline. External couplings are real where conductors are near and fields are strong. They leave signatures that repeat. They scale with the right. Knobs. They can be modeled. They can be predicted. That is the bar we will keep holding. In the next chapter, we bring the lens back to Earth and ask a tougher internal question. If the engine is rebalancing itself, what in the inner and outer core could be changing right now to send more power to tangled structures and less to the simple melody we love? We will meet reversed flux patches up close and watch how they grow. Drop through the mantle in your mind until stone gives way to a dark ocean of liquid iron. That ocean moves. Slow by human clocks, relentless by planetary clocks. Rotation organizes the flow into broad spirals that twist magnetic lines like taffy. When those spirals align, the simple global dipole grows and compasses smile. When they compete, energy leaks into tangled side structures and the surface field thins where the competition is fiercest. That is the setting for reversed flux patches, the core-borne features that cast long shadows up through the south. Atlantic and Southwest Africa. A reversed flux patch is not a hole. Field lines do not vanish. They loop back toward the core rather than joining the global pattern. Stack several of these counterflows beneath one sector, and the surface above feels weaker and more complicated. Satellites measure that weakness as a dent. Particle detectors feel it as extra hits. Navigation software sees it as a region where models need more care. The patch is the cause. The anomaly is the symptom. What makes a patch grow? Start with boundary heat flow. The core loses heat upward into a mantle that is not uniform. Beneath Africa and the Central Pacific, seismic maps show deep regions where mantle rock looks different from its surroundings. Differences in heat extraction across the core mantle boundary steer the iron ocean below. Where heat draws hard, flow can intensify and shear field lines into new shapes. Where heat draw slackens, flow can stall and give the map time to reorganize. Add the slow rain of crystals at the inner core boundary, which releases light elements into the liquid and drives buoyant plumes, and you have a cookbook for mischief. Now add rotation and curvature. In a spinning sphere, flow prefers columns roughly parallel to the axis. Those columns slide past one another and can set up shear zones that flip local magnetic direction. The flipped zones ride upward as reversed flux patches. At the surface, you do not see the columns. You see their footprints as changes in the smaller scale harmonics of the field. The dipole term eases, while the quadrupole and octupole terms grow more lively. Think melody down, counterpoint up. How do we know any of this, and not just believe it? Because the field at the surface carries the signature of its source. Analysts describe that field with coefficients that separate the broad dipole from the finer parts. Track those numbers over years and you can watch energy migrate from the main term into the side terms. Feed the evolving map into flow inversion methods, and you can infer patterns at the core mantle boundary that are consistent with reversed flux patches parked under southern Africa and the South Atlantic. Different teams, different math, same story. Then you sanity check with independent clues. Geomagnetic jerks show up as sudden changes in the rate of drift. Those jerks arrive when flow reorganizes, and they cluster in eras when the anomaly grows fastest. There is a second test. If patches are draining the melody under the South Atlantic, the pole should feel a tug in the north as the balance between the Canadian and Siberian lobes shifts. That is exactly what we saw when the pole began to sprint towards Siberia. The two stories are linked by the shared engine. Patches that grow under one hemisphere change the global ledger, and the pole follows the moving maximum, like iron filings follow a bar magnet through paper. What could be changing right now down there? The inner core is slowly freezing from the outside in, which releases latent heat and light elements into the liquid. If that release is uneven, it seeds flow asymmetry. The outermost core may host a thin layer, where composition differs from the bulk, a stratified cap that modulates how deeper currents couple to the boundary. The mantle above the core is not just a passive lid. Its hot and dense provinces can focus or diffuse heat, draw over millions of years, and steer gyres over centuries. None of this requires a nudge from space. It is a busy kitchen with many stoves. Prediction turns this picture from a story into a tool. If patches continue to strengthen under southern Africa, the anomaly overhead should grow and split further, with the secondary minimum deepening first. Ground stations in Namibia and Brazil should record secular variation that tilts more quickly. Low-orbit satellites should log higher radiation counts on crossings that clip the new minimum. The global model should show the dipole term easing, while specific higher terms rise in step. If those signatures fail to appear on schedule, the flow inversion must be wrong, and the cookbook needs a rewrite. Either way, the calendar keeps us honest. Uncertainty is part of the engine room tour. We do not watch the Iron Ocean directly. We listen through a magnetic stethoscope and reconstruct the patient from a changing waveform. That is why long clean time series matter. That is why open data and multiple pipelines matter. That is why jerks and recoveries earn attention. If a patch weakens and the anomaly relaxes more slowly than before, that could be the hint of threshold behavior. If it snaps back fast, turbulence may be in charge, and thresholds are a story we tell ourselves to feel clever. Here is the comfort in all this motion. The core can change on human time without placing daily life at risk. Satellites need smarter shielding and better schedules. Navigation needs timely updates. Curiosity needs patience and discipline. The rest of life carries on while the orchestra under our feet shifts parts. Next, we push from diagnosis to forecast. How do scientists turn today's field into tomorrow's map? And what new tricks in data assimilation and machine learning help us see a decade down the road without fooling ourselves? Forecasting a living magnetic field looks a lot like forecasting weather, only slower and deeper. You start with today's map. You estimate the flows below that can produce it. Then you let those flows run forward and see where the lines of force should move next. Along the way, you keep pulling in fresh measurements to nudge the forecast back toward reality. That loop is the heart of data assimilation. It is patience turned into math. The ingredients begin with observations. Satellites sketch the field from multiple heights and local times. Ground observatories record steady baselines through storms and quiet spells. Ship and aircraft surveys fill gaps over ocean basins and remote land. Archaeology and lava flows stretch the record backward by reading magnetism frozen into baked clay and rock. Each source has strengths and quirks. Assimilation gives them a shared table where every piece can help. Next come models that connect maps to motion. Physicists build simplified versions of the core that obey the same laws as the full geodynamo, but at coarser detail. Those models describe how flows at the core mantle boundary can shuffle energy between the main dipole and the smaller harmonics. Inversion methods use today's field to propose a family of plausible flows. Then, an ensemble of simulations carries those flows into the near future, each run starting from a slightly different guess to reflect uncertainty. Where the runs agree, confidence rises. Where they spread, humility grows. The loop closes when new data arrive. Instead of throwing out the old forecast, assimilation blends fresh measurements with the evolving state. If the model predicted that the anomaly over the South Atlantic would deepen by a small amount, and satellites confirm a similar sag, the next cycle proceeds with modest adjustments. If measurements disagree, the algorithm shifts the inferred flows to reduce the mismatch without breaking the rules of the physics. You can think of it as a guided drift, where observation is the guide and conservation laws are the guardrails. Machine learning joins this dance as a patient apprentice, not a magician. One role is to act as an emulator for expensive physics. A fast-learned surrogate can mimic how a slow core model responds to small changes in boundary conditions. That lets teams test many scenarios quickly and identify the few worth running at full fidelity. Another role is to mine patterns that hide in long records. Models trained on decades of satellite and observatory data can learn how small shifts in certain harmonics tend to precede kinks in the pole path or spurts in anomaly growth. These learned hints do not anomalies, replace equations. They sit beside them and whisper where to look. The dangerous temptation is to treat a learned pattern as a law. The cure is rigorous testing. Hindcasts are the gold standard. You pretend not to know the past 10 years. You train on earlier data. Then you ask your system to predict those missing years and you grade it without mercy. Good hindcasts earn trust. Bad ones send you back to the bench to change features, add constraints, or admit that what you hoped was a signal was just a phase in a noisy song. Communication is part of the craft. Forecasts do not arrive as a single line. They arrive as a cone of plausible futures with probabilities attached. Operators need that cone in plain language. A satellite team wants to know whether radiation exposure inside the anomaly is likely to creep up a little over the next 5 years, or might jump in a way that affects lifetime. A navigation provider wants to know whether the next unscheduled model update is likely or unlikely before the planned cycle. Clarity about confidence turns a plot into a plan. There are guardrails that keep us honest about limits. The core is chaotic in the strict sense. That does not mean random. It means sensitivity grows with time. At short ranges of a few years, forecasts can be sharp, where data are dense and models are well-tuned. At a decade, cones widen. Beyond that, we slip from forecasting to scenario building. The right answer, then, is not a claim. It is a set of if this then that maps that help decision-makers stress test designs against multiple futures. Hybrid methods are where the field is heading. Physics provides the skeleton so that every motion respects conservation and rotation. Data assimilation supplies the heartbeat that keeps the skeleton in step with the world. Machine learning adds reflexes that help the system react faster to subtle cues without inventing muscles that do not exist. When those parts are tuned together, you get forecasts that can call out a likely deepening of the secondary minimum under Southwest Africa, or a gradual easing of the Canadian lobe that keeps tugging the pole towards Siberia, and you get the error bars to match. The public face of this work shows up in familiar packages. The World Magnetic Model and the International Geomagnetic Reference Field are the quiet standards that phones, aircraft, and ships use. Behind those acronyms sit the loops we just walked. When an emergency update lands, it is because the assimilation saw reality sprinting and told the standards to lace up their shoes. Here is the takeaway worth carrying forward. Forecasting the field is not prophecy. It is disciplined listening with rules. The more diverse the data, the cleaner the rules, and the humbler the claims, the more useful the result. That is how we navigate a restless shield without pretending it will sit still for our convenience. Next, we bring the camera back to orbit and talk about living with the South Atlantic. Anomaly as it is now, and as it might be soon, from mission design to day-by-day playbooks that keep hardware healthy while the map keeps moving. If you fly hardware through the dent in the shield, you do not panic. You plan. The South Atlantic Anomaly is not a monster. It is a neighborhood with rough streets where good procedures and resilient designs pay off. Space agencies and startups alike already live with it. What changes now is the margin. As the footprint stretches and deepens, the playbook tightens. Radiation is the first language the anomaly speaks. Charged particles penetrate electronics and sometimes flip a 1 to a 0. Engineers call that a single event upset. Over years, particles also leave a cumulative dose that ages components. The countermeasures begin on the drawing board. Sensitive chips sit inside small vaults of aluminum or composite that add mass where it matters most. Designers pick parts that tolerate dose better, or they build redundancy so that a hiccup does not become a loss. Critical computers vote 3 times on the same calculation so that a stray bit cannot steal the result. Memory uses error-correcting codes that can spot and fix a flipped bit before software ever sees it. Software is the next shield. Every spacecraft carries a map of the sky that marks the anomaly as a do-not-loiter zone. Schedules avoid long integrations during crossings. Instruments go to a quiet state before entry and wake after exit. Star trackers expect more false speckles when radiation spikes and are tuned to reject them. Reaction wheels and gyros ride through short glitches without handing control back and forth. Watchdog timers reboot a stubborn subsystem quickly and bring it up clean while the rest of the craft keeps steady. None of these moves are exotic. They are muscle memory learned over decades and refreshed for each mission. Operations close the loop with data. Teams estimate how many minutes per orbit they will spend inside the PAR, contour where bit flips rise, and they plan around that number. They carry dosimeters and particle counters so that the craft itself becomes a scout for the next version of the map. If a crossing grows harsher than expected, the timeline shifts within hours. If a corridor softens at a given altitude, science time expands. The anomaly is not one shape for every path. Inclination, altitude, and solar cycle all matter. A 500-kilometer high-inclination platform sees a different pattern than a 400-kilometer vehicle in a lower tilt. Good operators treat the mask as a living document. The human side matters too. Mission planners include anomaly time in public dashboards, so scientists and the public know why an instrument rests when the world wants pictures. Astronauts on long stays learn the rhythm of crossings the way sailors learn tides. They secure activities that would be ruined by a sudden burst of stray counts. They turn other chores into productive filler during the quiet window. The goal is not to avoid the neighborhood, it is to pass through it with a purpose and without drama. Startups and university teams face a tougher trade. CubeSats and smallsats often fly commercial parts to save cost and time. Those parts can be more vulnerable. The answer is smarter fault management. A small computer can snapshot state often and roll back clean after a reset. Commands can be idempotent, so a replay does not cause harm. Data links can carry extra checksums. Attitude control can fall back to a coarse, safe pointing that keeps solar panels lit until the detailed sensors recover. With those habits, even modest hardware can survive repeated walks through the hot zone. There is a design myth worth retiring. More blanket always means more safety. Shielding helps, yet it also creates secondary particles when the blanket gets thick. The right move is targeted protection at the chip level and smart placement inside the spacecraft, not a uniform slab that adds mass and risk together. Radiation testing before launch teaches which parts need armor and which will ride it out. Forecasts turn practice into foresight. Assimilation models convert today's maps and years of counts into a near-term outlook. Will the secondary minimum under Southwest Africa deepen in the next 5 years? Will a given altitude band see a gentle drift or a sharper change? Operators do not need perfect prophecy. They need a cone of futures with honest error bars. That is enough to choose a star tracker with a better margin, or to add an extra layer of error correction to a memory bank, or to shift a science campaign away from seasons when crossings are longest. Even with care, surprises arrive. A geomagnetic storm can stack on top of the baseline and turn a routine pass into a spiky one. That is why anomaly masks are paired with space weather alerts in modern control rooms. If auroral indices jump, the team tightens limits and expands safe zones temporarily. After the storm, the baseline returns. You can feel how the separate stories we have been telling meet here. Space weather is weather. The anomaly is terrain. Pilots adjust for both. Living with the anomaly also advances science. Every bit flip is a data point for how the radiation environment is evolving. Every on-orbit dose sensor is a ground truth check for the models. Shared logs across agencies and companies make the next mission less blind than the last. In that sense, the anomaly funds its own understanding. The more spacecraft that pass through with open data, the faster the forecasts improve. This is the practical heart of our story. The deep core can move quickly on human time, yet most of the impact is absorbed by a thin band of orbit where we can plan, design, and adapt. That is good news. It means wonder and work can coexist. It means the right response to a growing dent is not fear, it is craft. Next, we pivot back to the visitor that shared the year with this dent and lay out a clean observing plan for the weeks after perihelion, so that amateurs and pros together can squeeze every lesson from 3i Atlas while it fades into the dark. Perihelion came and went in a midday heartbeat, and now the real work begins. Post-peak, 3i Atlas is a laboratory on a timer. Gas production will climb or falter. Dust jets will turn with the nucleus. The ion tail will answer every mood swing in the solar wind. This is the window when small, coordinated measurements turn curiosities into conclusions. No panic. Just craft and timing. First, we set the clock. Closest to the sun happened in late October at late morning coordinated universal time. In the first 2 to 6 weeks after that moment, sublimation often runs hot, as fresh surfaces crack and vent. If the nucleus has weak seams, small fragments may peel away here. If it is tougher, the light curve should rise gently, stall, and then begin the long fade. Either way, mid-November through December is prime time for trend hunting. Photometry is the backbone. Measure brightness night after night with the same filter and the same method. The goal is not a hero image. The goal is a clean, boring sequence where every point can be trusted. From that string, you read rotation hints on hour scales and production changes on day scales. If you're working with a modest telescope in a backyard, you still matter. Consistency beats aperture when the question is tempo. Share the raw counts, the comparison stars, and the weather notes. Others can stack and cross-check. 100 small eyes beat one big one when the target is fidgety. Spectroscopy. Layers in chemistry. The lines of water fragments, carbon monoxide, cyanide, and other tracers, sketch what ices are in play and how the balance shifts with distance. Early activity beyond 3 astronomical units flagged supervolatiles as suspects. Post-perihelion spectra can confirm the mix, or surprise us with new players once deeper layers are exposed. Even low-resolution spectra help if they are regular and calibrated. The trend is the message. Polarimetry is the truth serum for dust. The deeper negative branch seen at small angles before perihelion said fluffy grains and odd optics. Now we watch the phase curve on the way out. If the signature holds, the interior matches the skin. If it relaxes toward more ordinary values, the crust was special, and the core is planar. That is a clean falsifiable fork. Teams with polarizers on small scopes can contribute by repeating simple angle sweeps on a steady cadence. Tail morphology is the sky sketch of all this physics. The dust tail tells the story of the last few days of activity and spin. The ion tail tells you what the wind did in the last few hours. Watch for kinks that run down the ion tail like a ripple on a ribbon. Watch for disconnection events when the tail snaps and reforms after the wind flips its field. Mark the times and share them. Spacecraft between Sun and Earth will record the wind that caused the move, match ripple to gust, and you have a textbook in real time. Outburst watch keeps the drama honest. A true outburst looks like a sudden climb in brightness across many observers, followed by a slow relax as dust spreads. A single report that vanishes the next night is likely weather or processing. Call an outburst only when independent eyes agree, and when the coma shape changes in step. If a fragment appears, it will drift slowly and grow its own coma. That is rare and precious. If you think you see it, hold the claim, gather a second night, then speak. Patience is a power move. Coordination is how amateurs and pros become one instrument. Citizen networks can assign nights by longitude so the light curve never sleeps. University teams can host shared logs with simple forms that ask the same few questions every time. Professional observatories can drop time on polarimetry and high-resolution spectra at key phases and post quick-look results so others can adjust. Social feeds are fine for excitement. Repositories are where the science lands. Post your flats and darks. Post your calibration stars. Post your misses. A clean no is information. Safety talk is short because geometry already did that job. Closest approach to Earth remains far. The tail will never cross our path in a dense sheet. What matters for us here is learning how an interstellar comet breathes as it cools. Each good measurement feeds the models that will greet the next one with less surprise and more precision. There is a quiet gift for space operations in this watch. Every confirmed kink or disconnection in the ion tail that lines up with solar wind data is a drill for the pipelines that protect satellites. Teams can trace a disturbance from a comet image to a magnetometer spike and back. That rehearsal pays off when the driver is not a comet at all, but a coronal mass ejection aimed at Earth. The comet becomes a harmless sparring partner for the ring, where the real fights happen. So here is the plan you can carry to the backyard, to the control room, or to the classroom. Measure the light with care and regularity. Read the spectrum when you can. Sweep polarization angles on a schedule. Photograph the tails and time the kinks. Share everything with enough detail that a stranger can repeat your work. Then let the calendar do its work and watch the story emerge from the stack. Next, we pivot back underground and face a harder question with the same discipline. Could changes at Earth's surface and in its climate be nudging deep boundary conditions in ways that matter to the flow below? The numbers are stacked against it, yet the pathways are worth testing because they teach us how connected this planet truly is. Start with a picture you can feel in your bones. A continent wears a crown of ice tall as mountains. Rock bends under the weight like a foam mattress under a sleeper. Melt that crown and the mattress rebounds. Not in a day, in decades, to millennia. That slow spring back is glacial isostatic adjustment. It shifts coastlines by centimeters each year. It changes local gravity a little. It moves stress around in the crust. The question for our story is whether that surface reshuffling nudges the boundary 3,000 kilometers down where the liquid iron flows. Be honest about scales. The energy in the core is immense. The mantle between us and the dynamo is thick and stubborn, yet the planet is a single machine. Remove 1 trillion tons of ice from Greenland, and you change pressure above faults and magma reservoirs. Water follows the relief, fills fjords, and loads other margins. The crust flexes, the upper mantle creeps. None of this is magic. It is viscosity and time. Now ask what could carry a surface change deeper than everyday intuition allows. Heat is one path. Geothermal flux is not uniform under ice sheets. Some patches run hot where mantle structures focus warmth upward. Thick ice acts as a blanket and changes the temperature profile near the surface. Remove that blanket and you change the way heat escapes. The change moves downward slowly. Rock conducts heat like a terrible radiator. But over centuries, the perturbation can travel kilometers deep. The effect is small and local. Still, small and local is where boundary conditions begin. Pressure is another path. Ice is heavy. Take away hundreds of meters of it and you lift a load. That lift changes stress in the brittle crust right away and in the viscous upper mantle over time. Channels that carry melt at depth are sensitive to stress. A little more room here, a little less there, and flow reorganizes. If that flow affects how hot material approaches the base of the lithosphere, you have a lever on where heat leaks upward and where it stalls. Again, small and local, yet real. What about mass moving from high latitudes into the ocean? Sea level does not rise like a bathtub. Water piles up differently around the world because gravity and rotation set the shape of the surface. As the shape shifts, loads move across the plates and ocean floors. The redistribution is measured in centimeters and in slow years. It still adds to the pattern of stresses in the shell that covers the mantle. The mantle answers by flowing, very slowly, but it answers. Here is where discipline enters. The leap from these near-surface stories to the core is the longest in the house. The signal weakens at each step. Heat or stress, anomalies that begin under an ice sheet, must cross hundreds of kilometers of mantle before they can even reach the boundary with the core. By the time they get there, they are diffused and faint. The core is a roaring engine. A faint knock at the door is not a throttle. At best, it changes the shape of the doorway a little, so the honest baseline is probably not. Modern climate change is fast in human terms and already large at the surface. At the core, it is a whisper. That does not mean ignore the whispers. It means measure them and look for the few places where the geometry could amplify them. Under Antarctica, there are known hotspots and complex mantle structures. Under Greenland, the lithosphere is thinner in places than maps once claimed. These details do not overturn scale. They set the stage for good tests. What would a useful test look like? You would watch ice mass, sea level, and crustal rebound with satellites and ground stations. You would build mantle models that respect rock viscosity, that changes with depth and temperature. You would compute how heat flow at the core mantle boundary responds to surface loads, moving on decade to century rhythms. Then you would ask whether the calculated changes are large enough to steer flows by more than a rounding error. If yes, you would publish predictions with dates and places so that magnetic data can check them. If no, you would write that down too and give the field permission to move on. There is a faster route to humility. Rocks and pots remember heat. Boreholes show how past surface temperatures soaked downward over centuries. Those records prove that a century of warming has not yet reached far into the crust. If the crust has not felt the full step, the deep mantle certainly has not. That is a simple anchor that keeps speculation on a short leash. Yet the connected Earth keeps us curious. Floods affect groundwater. Groundwater affects seismic speed and conductivity in the upper crust. Conductivity affects how electromagnetic fields from above map into the ground. Even if the core is deaf to climate, the layers above it are not. They change how we read signals and how we design instruments. Climate moves the furniture in the room even if it does not touch the foundation. So, we hold two truths together without drama. Surface change is real and strong and fast. Deep change is real and slow and insulated. The bridge between them is long and lossy. If there is a narrow case where the bridge carries a faint but meaningful hint to the core, it will announce itself with numbers that line up across datasets and with forecasts that survive the calendar. That sets up our next move. Before we close the book on connection, we should define the kind of fingerprints that would actually force a rethink. Not vibes, not timing alone, hard signals that would make every skeptic sit up. What would count as a real link? If you want to move a debate from maybe to yes, you need signatures that survive every skeptical test. Not goosebumps, not a lucky timeline. Hard, layered evidence that connects sky to ground to core with the right power and the right delays. Here is what that would look like if a real coupling existed between an external driver and Earth's dynamo, and how we would know we were not fooling ourselves. First, a staircase in time. A disturbance would appear upstream in the solar wind where spacecraft sit, then in the magnetosphere, then in ionospheric currents, then as induced fields, in the crust and upper mantle, and finally as changes in the slow harmonics of the internal magnetic field. Each step would arrive with a lag that matches physics, not convenience. Minutes from wind to magnetosphere, tens of minutes to hours into ionospheric currents, hours to days into ground induction, months to years into core-sensitive signals. If any layer jumps the queue or runs early, the chain breaks. Second, phase discipline. Across multiple cycles, the deep response would line up with a repeatable driver signature. It would not be any storm. It would be this kind of driver, with this geometry, at this amplitude. For example, a specific multi-month pattern in solar wind, magnetic orientation or pressure that correlates with a specific drift in a named spherical harmonic of the internal field, with the same phase relationship every time it appears. No cherry-picking, no moving goalposts after the fact. The prediction is written before the next cycle and graded in public. Third, scaling that obeys mechanism. Double the driver, roughly double the deep response within error. If the proposal is electromagnetic induction coupling through the mantle, then regions with higher mantle conductivity should show stronger responses. If the proposal is pressure-mediated changes in heat flow at the core boundary, then the response should track regions where mantle structure focuses or relaxes heat draw. Geography, geology, and amplitude must rhyme. Fourth, separation of clocks. The internal field has its own rhythms: jerks, pole wander, slow exchange between dipole and side terms. A true external coupling would modulate that song without rewriting it. In the spectrum, you would see sidebands appear around known core timescales when the driver is active and vanish when the driver sleeps. That is how weak forcing shows up in a strong oscillator. If the supposed signal is just a rise in overall variability, with no structure tied to a driver clock, it is likely weather. In the core, not a whisper from above. Fifth, laboratory anchors. Conductivities of mantle minerals at pressure and temperature place limits on how deep external fields can matter. Any claimed pathway must pass those limits. If your math needs conductivities 10 times higher than measurements allow, the pathway dies. If your math needs stable, long-lived external tones, show the sky can actually produce them in the required band. Bench physics guards the gate. Sixth, replication across tools. Inversions of the internal field performed by independent teams with different regularization should see the same small harmonic wiggles tied to the driver. Ground magnetotelluric arrays that sense induced fields should echo the same timing. Satellite electric field measurements should register compatible changes. If only one pipeline sees the effect, it is not real yet. Seventh, persistence without the comet. If your claim rests on a single visitor, it will not survive. A true coupling lives in the environment, not in a cameo. It must appear whenever the driver pattern appears, across years and across different sky seasons. If 3i Atlas were your spark, the next interstellar visitor, or the next run of similar solar wind geometry, must replay the tune. No rerun, no case. Eighth, a null test that passes. Choose a window where the driver is absent but everything else is lively. The supposed deep response should vanish there. If it does not, you are watching internal variability in disguise. Null tests are boring. They are also where many beautiful ideas go to rest with dignity. Ninth, cost paid up front. Pre-register the analysis. Fix your filters, your band passes, your geographic masks, and your thresholds before the data arrives. Publish the full list of tests you will run and commit to report all outcomes, not just the exciting ones. When the day comes, you either hit what you called or you miss. Either way, trust grows. 10th, predictive utility. A real link buys something useful. It lets a forecast system reduce uncertainty on a named element of the internal field when the driver behaves a certain way. It lets an operator plan for slightly different anomaly exposure months in advance based on a driver index. If the only payoff is a headline, it is not physics. If it changes a map or a decision, it earns a seat at the table. Now flip the lens. What would kill the link cleanly? If high-cadence observations through a full driver season show no consistent phase relationship between external indices and deep field harmonics, the case falls. If scaling tests fail, the case falls. If the effect only appears after aggressive filtering choices and vanishes when methods change within reason, the case falls. If the geography ignores mantle conductivity structure or known reversed flux patch locations, the case falls. This checklist is not meant to raise the bar so high that nothing passes. It is meant to protect the rare yes from 1,000 almosts. If a coupling exists, even a fragile one, it will leave footprints that survive, method changes, travel down the staircase in order, scale with the right knobs, and pay rent in prediction. If it does not, we will have learned exactly why, and we will carry that clarity back to the larger story without apology. Which brings us to the close. 2 great threads shared a year. A restless shield beneath our feet and a visitor lighting a pale tail far away. The meaning of their timing is not cosmic design. It is an invitation to watch harder, to test cleaner, and to tell a story that keeps wonder and evidence in the same frame. One last chapter, then. We tie the threads, leave you with a map of what matters next, and ask you to stay in the chase with us. We began with a paradox that felt too neat to be real. A restless magnetic shield below and an interstellar visitor above, sharing a calendar page as if the universe wanted a headline. We pulled that feeling apart and put the pieces under light. Physics said the link was almost certainly no. Evidence agreed. Yet the journey changed us anyway, because it taught us how to look, how to measure, and how to stay curious without surrendering to stories that only feel right. Here is the map you can carry after the credits roll. First, Earth's magnetic field is dynamic by nature. It weakens, wanders, jerks, and sometimes flips across deep time. On our watch, reversed flux patches under southern Africa and the South Atlantic are steering energy away from the simple dipole toward more tangled structures. That is why satellites see a deepening dent, and why navigation models needed mid-cycle fixes. The engine is internal, the stakes are practical. We respond with better shielding, smarter operations, and frequent model updates. Second, space weather is weather. It batters the magnetosphere and lights the sky. It induces currents in power grids and whispers into the ground. It does not reach the core with the power or the coherence to steer the geodynamo. That boundary keeps 2 great stories apart so that we can respect each one on its own terms. We watch the auroral electrojets for operations and for beauty. We watch the slow harmonics of the field for climate-scale motion in metal far below. Third, 3i Atlas was a gift with no teeth. It reminded us that the solar system is a laboratory for plasma, chemistry, and chance. Its early water activity, odd polarization, and clean geometry gave professionals and citizens a shared experiment. It also rehearsed the muscles we will need when faster, stranger interstellar visitors arrive as surveys improve. Precision lives in how we plan the watch, share the data, and hold our claims until the calendar can pass judgment. Fourth, comparison widens comfort. Jupiter's moons, Mars's fossil magnetism, young exoplanets with electrified skies, each one stretches our models and makes Earth's surprises feel less lonely. The lesson is steady. Boundaries. Matter, conductors respond. Fields funnel energy into places we do not expect. That does not make every coincidence a clue. It makes every clue earn its place by scaling, repeating, and predicting. So what should you watch next? Watch the anomaly footprint over the South Atlantic and Southwest Africa. If the secondary minimum deepens and splits as forecast, the internal story hardens. If it relaxes instead, we learn something new about thresholds. Watch the next World Magnetic Model update window. If another unscheduled patch arrives, it will be because reality outran the 5-year beat again. Watch the flow of interstellar object discoveries as new surveys come online. A handful per decade will become a stream. With coordination, we can catch the next one earlier and learn more with less speculation. Watch the missions already en route. A European craft will settle into orbit around Ganymede and show us how a small dynamo breathes over years. An American craft will fly Europa, again and again, and let a salty ocean answer a magnetic metronome with uncomfortable detail. Their time series will feed dynamo theory and mantle conductivity maps that circle back to Earth in better priors and tighter inversions. Watch the quiet revolution in assimilation and machine learning. Hybrids that keep physics as skeleton and use data as heartbeat are already calling the next bends in the map with honest error bars. Most of all, watch how we work. Open data lowers the heat and raises the hit rate. Pre-registered analyses tame wishful thinking. Clean null tests earn as much applause as positive results. Communities that celebrate corrected errors build trust that outlasts any single plot or claim. That culture is not a side note. It is the instrument that turns wonder into knowledge. Where do you fit? If you fly hardware, bake the anomaly into design and operations now. If you analyze data, share your pipelines and your misses as well as your wins. If you observe the sky, join coordinated campaigns, and post the details others need to repeat your work. If you teach, show the staircase that real signals must climb and the fingerprints they must leave along the way. If you are simply curious, keep asking for mechanisms, magnitudes, and predictions that could be wrong in public. Coincidence, or clue, was the hook. The answer, for now, is coincidence with consequences. Not because a comet tugged the core, but because the coincidence pushed us to measure harder, model cleaner, and think together across boundaries. That is a story worth sharing. If you want the next chapter, the moment it breaks, tap like and subscribe, drop your questions and your city below, and send this to a friend who loves the sky but trusts the numbers. We will be here, following the data, keeping the wonder close, and letting the calendar decide.